All right, good morning. Here we are again for another lovely session of MENG 3310 Fluid Mechanics. So normally we don't record two lectures in the same day, but we were not able to hold a lecture on Wednesday due to some weather problems and some equipment failures that resulted from said weather problems. But here we are again. So I'm going to hold an extra bonus lecture today, and we'll continue right where we left off with more material on Buckingham pi theory. So let me discuss the determination of Buckingham pi terms. So determination of Buckingham pi terms, and we're going to use the method of repeating variables. Method of repeating variables. So determination of pi terms. So in the previous lesson, I explained what a pi term was. I gave an example of it, that kind of thing. But I didn't actually talk about how we actually find those things. And that's what we're going to talk about today. And we're going to use the method of repeating variables. Again, we'll be using the method of repeating variables, and we'll list a series of steps. All right, so I'm going to reference the same kind of thing I used last time, which again was, if you remember from the previous video, if you want to go back and reference it, we used delta PL equals a function of diameter, density, viscosity, and velocity. Okay, so we're going to be referencing this system as we work through our determination of pi terms. So the first step will be to list all variables that might describe a system, but they must be independent. And what do I mean by independent variables? Well, independent means that they cannot be expressed in terms of each other. They cannot be expressed in terms of each other. So for example, what if I had delta PL is a function of diameter, rho, dynamic viscosity, and kinematic viscosity nu, and also velocity v. This wouldn't work. Notice we have a problem here. I know that one viscosity can be expressed in terms of another. So, in other words, if we remember from previous lectures, that nu is equal to mu over rho. This isn't going to work. I can't, in order to be independent, I can't express one of them completely in terms of the others. So if you can, you know that you don't have truly independent variables. So mu and nu and rho are not independent. Now I could use nu and mu if I didn't have rho, but as long as I have rho in there, I can't use that as one of the variables. Are not independent. I have to eliminate one of them. I could very easily have both mu and nu in there, but I could not have rho. Are not independent since we can write them in terms of each other. Since we can write them in terms of each other. Of each other. All right, so that's the first step. We want to list all of the variables, or at least describe the system in terms of a set of independent variables. Next, my second step will be to express each variable in terms of its basic dimensions. its basic dimensions. In terms of its basic dimensions, so for example, delta PL, this has dimensions, and we looked at this a bit last time. ML to the -2, T to the -2. Diameter has dimensions of length. Density has dimensions of ML to the -3. O, mu, viscosity has units of ML to the -1, T to the -1, and velocity has units of, dimensions of. It's very tempting for me to use those words. I'm trying to be more precise with my language, but again, it's very tempting sometimes to use the words dimension and units independently, but I want to be very careful and say that this has dimensions of L to the, LT to the -1. So I do want to try to be very careful with my wording here. So that's our, that is our second step. 3, I wish to express each variable in terms of basic dimensions. In terms of the basic dimensions, oh, derp, that's me copying wrong, sorry about that. That's the danger of working on autopilot, I suppose. Okay, getting behind on myself. The third step, the proper third step, will be to determine the number of required pi terms. The number of required pi terms. And again here, I'm going to say k minus r is equal to 5 minus 3 is equal to 2. K minus r equals 5 minus 3 is equal to 2. All right, so I know here that I'm going to need 2 pi terms in this case. All right, now I want to select r pi terms. So, and I'm going to give some notes on how we do this. When I say select, I mean actually select the variable, select the pi terms. So for example, so I'm going to say select, so I'm going to describe it, then I'm going to work through the example. Select r repeating variables, I should say, sorry, not pi terms. Select r repeating variables. So again, r is the number of reference dimensions, and I want to select what I call repeating variables. And again, where r is the number of reference dimensions, where r is the number of reference dimensions, and let's see, a few notes on this. One, do not include the dependent variable, or the final variable, you might say, which in our case would be delta PL. Delta PL. Delta PL. So I don't want that to be one of my repeating variables. Second, all reference dimensions must be present in one of my repeating variables. Must be represented in the repeating variables. That doesn't mean they have to be present in all of the repeating variables or in each of the repeating variables, but all reference dimensions must be represented at least once. So for example, here, if I'm using an MLT system and I find that my variables have MLT, if I list my, if I select my So if I have a system like the one I've been working through, where all three of these are present, well, in my particular repeating variables that I select, and when I say repeating variables, what I mean is those repeating variables will appear in all of my pi terms. They repeat in all of the pi terms. So MLT must be present among my repeating variables. My repeating variables among my repeating variables. And then C, each must be dimensionally independent. Each repeating variable must be dimensionally independent. In other words, one, they cannot be combined to form one. One another. One another. And two, they cannot form a dimensionless number by themselves. So I want to eventually use these to create dimensionless numbers. But among my repeating variables, I don't want there to be any way to use just those repeating variables to create a dimensionless pi term. So we'll have both repeating and non-repeating variables. I want to choose repeating variables such that I have to use the non-repeating variables in order to in order to create pi terms. So I'll work through that here. I'll give an example of this. So let's look at this. So I know in our case that we have 5 variables. And we know that we have 3 reference dimensions, and 3 reference dimensions. Refdims. And so I need to choose 3 repeating variables. That's what the R stands for, fundamentally. Well, I guess it could stand for both reference dimensions or repeating variables, kind of doing double duty. Repeating variables. So I need 3 repeating variables. So let's look at some possible solutions. Or some possible options. Well, what if I wanted to try, okay, I could say diameter maybe. What if I said diameter, viscosity, and velocity? What if I decided those are my repeating variables? Would that work? Let's find out. Well, this has, diameter has units or dimensions of length. Viscosity has, I keep saying units. Viscosity has dimensions of m, L to -1, T to -1, and L, D to -1 for velocity. Well, let's think about this. Well, let's look at this. Well, we have the 3 conditions previously. So the first question is, did we use the the dependent variable? Well, we didn't. We didn't use delta PL, so that isn't present here, so that's good. All reference dimensions are present. So we got an M, L, and T. That would work. And there doesn't appear to be any way I can combine these to create something dimensionless. Like I can't there doesn't seem, just looking at these, so again, A, we seem to be good, B, we seem to be good, and C, we seem to be good. There doesn't seem to be any way I could maybe multiply these together or divide them together. And the only possibilities are multiplying and dividing. There doesn't seem to be any way I could combine these together that would produce a dimensionless term. Okay, so what else do we have? Let's try something else. That's one possibility. That seems to be one possibility. Other possibilities, I could say, what if I tried diameter, density, and velocity? Well, I have length. So again, diameter has dimensions of length. Density has units of m, or dimensions of m, L to negative 3. And viscosity has dimensions of, let's say here, velocity has units of L t to the negative 1. L t to the negative 1. So, well, clearly here, again, condition B is all reference dimensions are present. So we have all the reference dimensions. So delta PL isn't there, so our part A is correct or satisfied. B, we have all reference dimensions present. And C, obviously we can't use this one. Or sorry, obviously we can't cancel out because there is literally no way I'll be able to cancel these out because there's only mass. Mass is only present in one of these. So there's no, if mass is only present in one of them, there's no way I can divide or multiply density by diameter and velocity to cancel everything out. There's just no way because it's only because the mass dimension is only present for the density. So that one might work. So there are many options with these. There are often many different options you could use. So, for example, another one, what we might say, what if we looked at a combination of, what if we looked at diameter, density, and let's say viscosity again. What if we looked at this one? This would have units of length, of course, m, mass, length to negative 3, and this would be m, L to the negative 1, T to the negative 1. And this would also seem to satisfy all of these. There's no way we could cancel all of these out, so A would be good. All the reference, so the delta PL isn't present, so that's A is good. All the mass, length, and time are all present, so that would be good. And there doesn't, also with this one, there doesn't seem to be any way I can, well, there definitely isn't any way I could cancel these out because time is only present for the viscosity term. So we could use, so this would be another one that would work. Let me give you an example that would not work. What if I had a system, now what if I looked at, say, a stress here, and I had maybe a slightly different problem where I had stress, sigma, and if you work through it, you find that the units for stress are m t to the negative 2, something like that. So that wouldn't work. Sorry, what if I had something like, then density, or sorry, not density, viscosity, having units of m, L to the negative 1, T to the negative 1, or, and velocity is m, T to the negative 1. So what if I had a system where I tried to see if I could use repeating variables of, now this one isn't present for our problem, but this gives a good example of one that wouldn't work. Where if I had stress, viscosity, and velocity, well, if I put these together, I can, what if I do sigma over mu v? Well, sigma over mu v, this would actually come to, it would come to 1. All of the dimensions would cancel out. This would be dimensionless. So this would be an example of something that we could not use. Cannot use sigma sigma, mu, and v for repeating variables. So this can take time. This is the hardest part. I mean, selecting your repeating variables, a lot of it is trial and error. It's not as trial and error as it could be, but for just picking random pi terms out of the blue, but it is a bit of trial and error, and it can be tricky. So it takes patience. It can take a while. This is the most frustrating part of selecting pi terms. Now, just for my example, so just going forward here for my example, let's use, I'm just going to use a diameter, maybe diameter, rho, and velocity. diameter, density, and velocity. And why I might use those? Well, those are pretty fundamental quantities. Those are fairly easy to work with, but easier to work with density and velocity and diameter than it might be for viscosity. But again, these are my repeating variables, so we'll see. Again, because these are the ones that are going to appear in every one of my pi terms. So if I have something that's really difficult to work with, like viscosity perhaps, or maybe that's not difficult to work with, but anyway, you can play with it. I like using diameter and density and velocity, but you can use what you wish. For example, on an exam environment, if I give you a problem on Buckingham pi terms, there may actually be more than one correct answer. So these are always kind of difficult for me to grade because I have to go through in detail, and actually I can't just check if you have the right answer. I have to check if your answer works. So there are many possible answers to these types of problems. So when I give you homework, I'll eventually post homework solutions on the site, but that will be one possible solution of many. So I can't just say, oh, there's only one. Now, for some very simple systems, there is only one possible answer. But for more complex systems, you can actually have a whole, a menagerie of possible pi terms. Man, there aren't many opportunities in fluid mechanics I get to use the word menagerie, but I found a way. Anyway. So then for our final step, I want to form pi terms. Form pi terms. And to do this, I'm going to multiply non-repeating variables to get a dimensionless number. To get a dimensionless number, and however, though, we can raise the repeating variables to any power. So in our pi terms, the non-repeating variables, we want to keep them as simple multiplications, but we can raise the repeating variables to any power. But then B, again, the non-repeating variables must be raised to a power of 1. Non-repeating? Great. Repeating variables must be raised to a power of 1. And of course, by definition, because they are non-repeating variables, each pi term will have, or I should say each non-repeating variable will appear in only one pi term. That's a definition of a non-repeating variable. Each non-repeating variable will appear in only one pi term. So, for example, in our case, I want to finish working through this example, and we use these to find our pi terms. So, for example, in our case, our repeating variables, we have repeating variables and non-repeating variables. Repeating and non-repeating variables. And let me look at and so I will write out the dimensions as I go because these are pretty useful. And I'm using diameter, density, and velocity as my repeating variables. Dimensions of L. Again, this all comes down to the dimensions. M, L to the -3, and L, T to the -1. Our non-repeating variables are going to have delta PL, has dimensions of m L to the negative 2 t to the negative 2. Mu will have dimensions of m L to the negative 1 t to the negative 1. M L to the negative 1 t to the negative 1. And so basically, now remember, we determined that we were going to need 2 pi terms, right? And so let's think about this. We need 2 pi terms. And oh, look, we have 2 non-repeating variables. This is not a coincidence. So basically, if you work through this, you will find that each pi term will have only one of the non-repeating variables. Only one of the non-repeating variables. Let's see, so again, because if we remember before, we said that the number of repeating variables is going to be equal to the number of number of dimensions, right? And we said previously the number of pi's is equal to k minus r, right? Where this is the number of variables minus the number of repeating variables, right? So by definition, if k is the total number of variables and r is the number of repeating variables, well, the number of non-repeating variables is also equal to k minus r. So the number of pi terms will always be equal to the number of non-repeating variables. You give each pi term one and only one non-repeating variable. So we're going to give each pi term one and only one non-repeating variable. So let's start with pi 1. Let's see, so start with pi 1. And I know that delta PL has dimensions of m L to the negative 2, t to the negative 2. And let's see, so we just start building these things. And again, I know that delta PL has to remain a multiplication. It must have a power of, it must be taken to the first power. I can't get fancy with this. Anything else, all the other terms I can do whatever I want with. And actually creating the pi terms can also be tricky because it's a certain amount of trial and error, figuring out what kind of power you need to take them to, that kind of thing. Or you could use some matrix methods if you want to get some simple solutions or to guide your analysis if you wished. But let's see. And it can get quite complex in certain cases. So what happens if I were to try, maybe dividing by row? Let's try working with row. And so again, I need to find, so I know I'm going to have delta PL, but I'm also going to have my 3 repeating pi term, sorry, 3 repeating variables. So I already have delta PL, but I also need to work in here diameter, density, and velocity. So I need to find some multiplicative combination of these that will allow me to get a dimensionless term. And so if I, what did I do here? I screwed that up. Okay. So then delta PL over rho, this would have dimensions then of m L to the negative 2, t to the negative 2, divided by m L to the negative 3, and that would come to t to the negative 2 over L to the negative 1. So we've simplified a bit. We've made some progress. What if I then multiplied by d? So I want to get rid of this. Maybe if I multiplied by d, I could get rid of some length here. Something like this. So this would have units of, well, let me verify this really quickly here. If I did that, I would have t to the negative 2 divided by L to the negative, let me think about that. That doesn't quite make sense, does it? Divided by, that would actually be to the positive 1, wouldn't it? So actually, I think that's not quite right, is it? That's not quite right. So that would actually, sorry about that, that would be t to the negative 2, well, actually, no, I said over t to the negative, I said over L to the negative 1. That's correct, or just L over t to the negative, or just L over t squared, right? Something like that. But anyway, what if I multiplied by diameter then? Delta PL over rho times diameter. What would I have units then? Well, I would have, if I kept that t to the negative 2 over L to the negative 1, and then multiplied by L, well, now I would have L squared times t to the negative 2. Oh, look what that is. That's equal to L squared over t squared. Or that has the same units as velocity squared. So I know then that delta PL over rho times diameter has the same units as velocity squared. So to form the dimensionless term, I just divide them. So if I wanted to form a dimensionless number, I can simply say pi 1, my first pi term, is going to be equal to just this divided by this. So delta PL times diameter divided by rho v squared. Rho v squared. And notice, look, I have my delta PL present. It has a power of 1, and the rest I just have all of my repeating variables represented. I could take them to any power I wanted, anything that would work, that would produce a dimensionless number. All right, so very useful. Now let's get pi 2, the second pi term. So pi 2, well, let's see, viscosity has units of, I need to use viscosity as my non-repeating variable because I already defined my other repeating variables. So this has units of m, L to the negative 1, t to the negative 1. So let me try first dividing by density. And the reason I'm doing this is I'm going to try to eliminate as much stuff as I can right off the bat. So if I divide viscosity by density, I will get m, L to the negative 1, t to the negative 1, divided by m, L to the negative 3, which that comes to t to the negative 1 over L to the negative 2, which is simply L squared divided by t. So getting warmer, getting better, getting closer, hopefully. What happens if I divide by v? Now, obviously, I make this look easy when I'm doing it, but I already have the, the everything written out in front of me, so that helps. But in reality, this is a certain amount of trial and error, so don't be frustrated if you can't just look at it immediately and determine it. This takes some practice, and it takes, more importantly, it takes some time. Even if you're a practice at it, you have to bang your head against the wall a little bit until you actually find a combination that will work. So if I do this, I would have the same L squared over t multiplied by 1 over LT to the negative 1, which comes to simply L. The t cancels out, and I'm left just with L. And then I have to do something with the diameter. Well, that's easy. If I just divide everything by d, suddenly I'll get a dimensionless number. So I have my same rho v d. Well, that will have units of, well, all this has units of length. So if I divide by d, which is diameter, which is also length, I just get 1. There we go. And so then my pi 2, my second pi term, can be simply mu divided by rho v, or rho dv. Again, my non-repeating variable, in this case my viscosity, had to be in the numerator and had to have a power of 1. So it must have a power of 1. It cannot have a negative power. It cannot have a power other than 1. It must be positive 1, and end of story. So those are our 2 pi terms. Now let us summarize. So I'll just end with a bit of summary of our system here. Well, I know that I can reduce my system now to this relationship. I can say that pi 1 is equals some function of pi 2. And this would be, in our case, delta PL d over rho v squared equals some function of mu rho dv equals some function of mu rho dv. Or I could actually invert this even if I wanted to. There's no reason I couldn't say, there's no reason I couldn't flip this around and maybe even flip it around. I could say something like, because these are dimensionless, if it were more convenient for whatever reason, now in creating the pi terms, I want to make sure that this appears in the numerator as 1, but once I have them, if it's more convenient, there's no reason I can't do something like this. Delta PL over rho v squared. Again, because these are all dimensionless, there's no reason I can't just say, oh, this is a function of rho dv over mu. And then my resulting function would be very different, but there's no reason I couldn't do this. So, what have we done? Well, besides getting lost in the woods a bit, we have collapsed our system. We have collapsed 5 variables into 2. We have collapsed 5 variables into 2. So previously we had all of those 5 variables, 4 independent variables and 1 dependent variable, and that would have been an experimental nightmare to determine. As we saw, if it's to the power of n, which is not improbable, we may have had hundreds of thousands or even millions of individual trials that we would have to physically do. When I say trials, I mean literally build an experiment and try it with different inputs. I would have to do that millions of times. Just absolutely, completely impractical. With 1 input and 1 output, 1 independent variable, 1 dependent variable, suddenly I have something I can actually create an experimental regime to do. I can just have a section of pipe. I can experiment with different values of this variable and see what kind of, I can put in different values of this pi term and see what kind of values of the other pi term I get out on the other end. All right, so I think that'll finish up for today. We'll be discussing this more next time, but that will conclude for this lesson today. That will do it. Thanks for watching, and as always, thank you.